Hello everybody, in this video we're going to talk about the second thermal radiation law, the Stefan Boltzmann's law. This law is going to relate the temperature of an object to how much energy it's giving off. And how much energy that is giving off is really telling us something. If we're talking about the stars, how bright is that star? How much light is it giving off in total? So a critical part of astronomy, and really amazing, that if we know the temperature of an object and how big it is, then we can really tell you how much energy it's giving off, how bright it intrinsically is, which is a really powerful thing to know. All right, so let's go ahead and jump in. The final thermal radiation video and Stefan Boltzmann's law. This one is a little bit more intimidating than Wien's law at first pass, but hopefully you'll see that it's a little bit easier to work with if you can only remember a few smaller things. So bear with me and we'll break this down into smaller parts to digest it. Before I actually start reading off and stating what Stefan Boltzmann's law is, let's take a look at what we're talking about. So again, we're still talking about thermal radiation. And when we're talking about thermal radiation, we're always picturing a black body, our perfect thermal radiator. So here is our black body spectrum, which gives us the wavelength and then how bright each wavelength is. And you can see this nice curve right here. And for a temperature, every temperature has a unique curve. When we are talking about the size of the curve, how big it is, what are we really talking about? If we're talking about the area underneath this curve, what are we adding up? Well, we're adding up all the ultraviolet light, so all how bright this object is in the ultraviolet. We're adding up all the visible light, and we're adding up all the infrared light and all the other parts of the electromagnetic spectrum as well. So we are summing up, we're adding up all the light that something is giving off. Light has energy. So really what we're doing is we're just adding up all the energy an object is emitting. And that's what we're working with this Stefan Boltzmann's law, is how much area is there under this curve? For a given temperature, how much energy is something emitting? So the light version of the Stefan Boltzmann's law, the one that you'll work with on quizzes and exams, is that the energy is proportional to the temperature raised to the fourth power. So that means that the temperature goes up, the energy goes up, is proportional to, directly proportional to, but it's directly proportional to the temperature raised to the fourth power. So let's consider, here I have two objects, two juggling balls. Let's just say that this is we're close to about 80 degrees Fahrenheit in here. It's much cooler than that, but so let's just say that this one is 300 Kelvin, and let's make this other one twice as hot. So this, imagine that this ball is 600 Kelvin, 2 times hotter, which by Stefan Boltzmann's law tells me, okay, I'm always thinking proportionally, so I'm going to go with how many times it got hotter and then apply the Stefan Boltzmann's law to that. So 2 times hotter, and Stefan Boltzmann tells me that energy goes with temperature to the fourth power. 2 to the fourth is 2 times 2 is 4 times 2 is 8 times 2 is 16 times more energy. So if this ball is twice as hot as this one, it's emitting 16 times more energy. That's amazing. Now let's imagine that I make it 10 times hotter. So it'd be about 3000 Kelvin. That's the same temperature as the surface of a cool star. Probably not a safe thing to have in my room. So if this is 10 times hotter, then how much more energy is it emitting compared to this ball? 10 to the fourth times. And 10 to the fourth is 10,000 times more energy? I definitely wouldn't want to be holding that, and I don't think I'd really have much of a face anymore if I was holding something that was 10,000, giving off 10,000 times more energy than this currently is. That would be pretty dangerous. But that's just to show you that you change the temperature a little bit, and Stefan Boltzmann is saying you're going to be giving off a heck of a lot more energy. In fact, the energy is proportional to the temperature raised to the fourth power. So notice here, just to remind you that temperature to the fourth is temperature times temperature times temperature times temperature. So how did I get that 16? Remember I said twice as hot? I did 2 times 2 is 4 times 2 is 8 times 2 is 16. But notice Now, if we're going to be thinking about this, so what are we talking about? We're talking about something emitting energy. Well, it's constantly emitting energy all the time, right? So I really wanted the total amount of energy that something is giving. I'd have to say, well, for how much energy over how much time? Because if it's constantly emitting energy, it's going to emit a lot more energy in total over 10 minutes than it will in 10 seconds. So really what we're talking about is the energy that something emits every second. Just some standardized way to think about it. So it's emitting this much energy every second. And now I want to talk a little bit, notice I've put this box in green, about the units that we use for these whenever we're talking about this Stefan Boltzmann, where we're talking about energy and energy per second. So the SI unit for energy, something that doesn't really come up in this class at all, but the SI unit for energy is the joule. What we're going to be talking about most of the time is energy per second. So how much energy, how many joules is something emitting every second? That's technically what we call a power, because power is energy per second. And whenever we're talking about the energy per second, the SI unit for that is the watt, something that you're probably already familiar with because you know light bulbs. You have a 40-watt light bulb, you got your 60-watt light bulb, you got a 100-watt light bulb. What does that tell you? It's telling you how much energy that light bulb is emitting every second. How bright is that light bulb? You emit more energy every second, you're going to be brighter. So really, we're talking about how many watts something is emitting is proportional to the temperature to the fourth power. Okay, so that's the simpler version, and we'll play around with that. Let's go ahead and consider this a little bit more. So here I have my iPad, and it has a certain amount of area. It has a temperature, say 300 Kelvin. So I could figure out, oh, well, that means that this iPad is emitting so much energy every second, so many watts per second. But if I had a second iPad, it would be emitting the same amount. So I'd have this iPad and another iPad right here. We'll use a stand-in of something that's roughly the same size. So same size, same temperature, means it's going to be emitting the same amount of energy every second, right? So if I consider both of them together, a bigger area, they're going to be emitting twice as much energy. If I had a third one, so iPad, 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 in total, those 3 iPads would be emitting 3 times as much energy in total than just a single one. So buried in all of this is the surface area of an object. How much area is there? So if we really want to talk about the total energy, if we want to get rid of this proportional to and put an equal sign, we need to know the size of the object, what its surface area is. So our full version, that'll give us a total amount of energy per second, needs to account for the total area of an object. And that allows us to get rid of this proportional to and change it to an equal sign. And this is, we're adding on little bits here. So if I need to introduce a new term. This one is a little bit scary, or at least scary sounding, but it's not that bad. We can picture energy per second. That's like a light bulb, it's watts. But we have this term called radiative flux. Scary sounding, but really all it's doing is it's telling you how many watts are passing through, say, an area the size of this iPad every second. So I have this light behind me, it's shining, it has a certain amount of energy that's going through this or hitting this iPad, this area, every second. So the radiative flux is going to describe how much energy per second, how many watts are passing through some standard unit of area. So maybe it's something like how much light is passing through, say, 1 square inch. So it'd be the watts per square inch. Or maybe it's going to be an area of 1 foot. How many watts per square foot? Or we use the metric system here, and we typically use a meter. So I could draw a box that's 1 meter by 1 meter. And we could consider how much energy is passing through that box. That's 1 meter by 1 meter, a meter squared. So it'd be the watts per meter squared. And then we're talking about a radiative flux. So we need the area, and the radiative flux term is the one that takes care of it. So it's the total energy emitted every second per square meter of surface. So it's how many watts, energy per second, joules per second, how many watts per meter squared. This allows us to get the full version of the Stefan Boltzmann's law, a more powerful version, the one that has an equal sign. We have to use the radiative flux because we have to account for that area. Okay, so normally, or most of the time, we don't want to always say radiative flux, radiative flux, radiative flux. Especially if we're writing things down, we'll just call it the flux. And we know that we're talking about the radiative flux. If you hear an astronomer say flux, they're talking about radiative flux. So the flux is equal to temperature to the fourth power. Hey, that part's still there. So the energy is still directly proportional to the temperature to the fourth power. But the radiative flux equals temperature to the fourth power times some number that we give the lowercase Greek letter sigma. Where notice this is in red, so don't commit this to memory. This number that we are representing by the lowercase Greek letter sigma is called the Stefan Boltzmann constant. It has a value 5.67 times 10 to the negative 8th, and the units on that would be watts per meter squared per Kelvin to the fourth. But don't worry about any of that. It's just some number. Just like when we worked with gravity, we had that big G, the universal gravitational constant. That was just some number. This is just some number. It's a different number. It's a different physical constant of the universe, the Stefan Boltzmann constant. I'm not going to have you actually go through and calculate fluxes in class, especially on quizzes and exams. You'll never have to tell me what the flux is, what the watts per meter squared that something is giving off. I'm not going to have you calculate that, although I will show it in this video for instructive purposes. So you don't really need to know the value of sigma because you're never going to have to calculate that. We're to always think proportionally, so we can just compare one object to another object and talk about how much energy one object is giving off compared to another object, or really how much energy per square meter, so the radiative flux of one object compared to another object. So that seems like a lot of work with a lot of confusing stuff. Why go through all this pain? Why am I spending so much time in this video to explain so many new concepts? It's because it's extraordinarily powerful. Because now, if we know the temperature of an object, which, you know, maybe we could observe its black body spectrum, find its peak, and use Wien's law to determine its temperature. So we can, if we know the temperature of an object and how big it is, so the sun is 5,800 Kelvin, I could calculate the total surface area of the sun. It has a radius of 696,000 kilometers. Then I could calculate the total amount of energy the object is emitting, in this case, the sun. I could tell you how much energy per second the entire sun is emitting. I could give you the wattage of the sun. How bright of a light bulb is the sun? I could do it for any star if I know its size. I could do it for a planet and know something about the energy balance of how much energy is being emitted by that planet. All of these are really, really fundamentally important if we want to understand stars and planets. I'll use the example of a star. So if we can go ahead, if we know the size of the sun, so we can calculate the total surface area, we know the temperature, which we can get from Wien's law, it has a temperature of 5,800, then we could calculate how much energy per square meter the sun is emitting, multiply it by the total amount of surface area, get the total energy that the sun is emitting every second. What watt light bulb is the sun? And that comes out to be roughly about, let's see here, what is it? It's 3.828 times 10 to the 26 watts, I believe. I don't have that number memorized. But that's a huge amount of energy. And that amount of energy that the sun is emitting must be the amount of energy that the sun is generating. And the sun is generating that energy through nuclear fusion in its core. So just by determining the total amount of energy that the sun is emitting, using these thermal radiation laws, we have discovered something fundamental about the sun itself. We have determined the amount of energy being produced by nuclear fusion in the core of a star. We can figure out, we can see how much power, how much energy is being generated by a star through the process of nuclear fusion. And we can look at any star. If we can determine its size and measure its temperature, then we know something about what nuclear reactions are going, what is powering the star itself. All this from the light in these thermal radiation laws. That's incredibly powerful. That's why I've spent so much time going through all of this. And let's go ahead and put this all together in what I call the astronomer's version of the Stefan Boltzmann's law. And I know another new term. So the term luminosity, which we usually just designate by the letter L, is just the total energy output per second of a light source. So for the sun, the total energy output of the sun is some number of watts. That is the luminosity of the sun. The luminosity of a 100-watt light bulb is 100 watts. So it's just the total energy output every second of a light source. That's what we mean when we say luminosity. So that's accounting for the total energy emitted per second, hey, it sounds like Stefan Boltzmann, over the entire surface area. So how many joules per second a star is giving off. So that's really just how many watts a star is emitting. So we talk about the energy of a star and its watts. How many watts is that star? What is that star's luminosity? That's a fundamental property of stars. We could do the same thing for planets as well. But notice that this is the total energy output per second. If I were to take the luminosity and divide it by the area, say the total surface area of a star, I would have the luminosity per area, which would be the energy per second per square meter. That sounds suspiciously like radiative flux. A luminosity divided by the surface area is the energy per second per square meter. That is radiative flux. And we now know the Stefan Boltzmann's law gives us a way to calculate the radiative flux. It gives us the radiative flux. So the luminosity divided by the area is the radiative flux. This is going to give us a way to relate the luminosity, the total energy output per second of an object like the sun or a planet, the planet Jupiter, to the Stefan Boltzmann's law, one of these thermal radiation laws. Going to give us a way to relate the energy of a star and energy output of a planet to these thermal radiation laws. So we have luminosity divided by area equals the flux. What I could do is I could go to a more full version of the Stefan Boltzmann's law. So luminosity divided by the area would equal the flux, which is sigma t to the fourth. Thanks, Stefan Boltzmann. Where I could just get rid of that area, I could say the luminosity equals the area times sigma t to the fourth. So I can get the total luminosity equals this equation right here. This is what I call the astronomer's version of the Stefan Boltzmann's law. Notice that it's still the energy per second luminosity is proportional to the temperature to the fourth power. But we have the total energy output, the luminosity is proportional to the surface area of the object. And then we have our normal Stefan Boltzmann, the light version. Total energy output, the luminosity, is also proportional to the temperature of the object raised to the fourth power. That's everything we just talked about put into a single awesome equation. This gives us a way to determine the total energy being emitted by celestial objects like stars and planets. If you know the temperature and you know the size, then we can calculate the total energy output. We can get a measurement of how truly bright an object is. Which means that all of this work has given us a new measurement tool for the universe. Wien's law became a thermometer for the universe. Find something that's like a black body, look at its black body spectrum, figure out where that peak is, and boom, you've measured its temperature. Stefan Boltzmann is giving us a brightness sensor for the universe. It's telling us how bright things are. It's telling us how much energy the stars themselves are producing, which is related to how stars function. Again, just all from the light. And I'll just go ahead and quickly mention this is all green, but if you really start wanting to play with this, then you might want to actually, instead of just having the surface area, what is the surface area of a sphere? And stars and planets are spherical in shape, 4 pi r squared. So you could take this equation and get rid of the area, put 4 pi r squared instead. You get this equation that relates the luminosity of something to the size of something, the radius, and the temperature of something. In Astronomy 152, we're going to come back to this because this is an extraordinarily powerful equation in astronomy. All right, so I know I went way beyond what we typically are going to be doing with the Stefan Boltzmann's law in this class, but I did that for a reason so we could get to see how powerful of a law this is. I'm going to save doing examples for its own video. That way you don't have to go through all this, feel confused by all the new terms. You can go watch a separate video to see me work through examples of this. So I'll be back with a video of examples of using Stefan Boltzmann's law. Thank you for tuning in.